Hey guys, it is often said that good features are what make or break models' performance. We have been saying this multiple times in the previous video. Feature transformation is a crucial step in machine learning pipeline. We have started a new series, a playlist of videos to understand everything about feature engineering. And we have already seen multiple different feature engineering techniques like data cleaning, imputation techniques, categorical encoding in the previous videos. If you have not seen that, please watch those videos first. This video specifically, we are going to talk about feature transformations and what are the different transformation techniques. In this video specifically, we're going to see the demo, the hands-on, how do I do the feature transformation using scikit-learn and the Jupyter Notebook. I'm going to keep the video link in the I button, and the Git repository that I have used to create this demo is also in the pinned comments, so please find that out if you want to try it on yourself. By the way, if you are new here, I am a mentor in the field of AI and machine learning. Started my journey long back, 12 years before as a mentor, and during this time, I got exposure to multiple technologies starting from Java to Python to data science and obviously AI. I have been helping corporates understand and implement applications, especially in Python data science. Alright, let's deep dive and understand how to perform different transformations using scikit-learn. Make sure to watch this video till then because we're gonna see every type of transformation with the demo. So let's get started. Hey guys, welcome to AI with AI. This side Asif Imnad. If you remember from our previous videos, I have discussed about three main types of transformations: function transformer, power transformer, and the quantile transformer. Why do we use transformers? Because the data, raw data which we get may not be in the good shape and the size. It is not normally distributed. It is positively skeeved, it is negatively skeeved. The range of the data in the another column are relatively high. That is why in the algorithms like k-nearest neighbor, linear regression, support vector machine, k-means, wherever you see a distance-based algorithms where we need to calculate the distances, they will give more weightage to the features with the large values because the distance is calculated with value of data points to find out similarities between them, right? If we feed data with the different magnitudes, meaning there is a huge variance between two different features, two different columns, then it will be way hard to converge to global minima. And that's why values of same range becomes less burden to algorithms to learn, right? So in the transformation, we transform the values of the features without losing their intrinsic value, making data more Gaussian, more distributed, more normalized so that algorithm can learn faster, easily, and we will have less variance. And we already discussed it in the previous videos, right? So for now, in this video, we are gonna see 5 demos of each type here. For function transform, we are gonna see a demo for log, reciprocal, and the square transform. Similarly, the one of the most popular transform that is used generally is power transform. That's Box-Cox transform and Johansson transform, right? And yes, this is what I discussed, right? Why and where to use. Transformations are mainly used where machine learning algorithms are distance-based algorithms like linear regression, logistic regression, k-nearest neighbor, SVM, k-means. And by applying these transformations, these skeeved variables can be converted to the normal distributions to increase the performance of our model. Alright, so how are we gonna do this? By using scikit-learn library here. And there are 4 simple steps that you see. It's very easy to use transformations. If this is very much clear to you, let's understand how to use these transformations with scikit-learn. There are 4 simple steps here. If you see, we're just gonna import the function transformer as you see here from the scikit-learn. After that, in the second step, we are gonna initialize the function transformer, some variable equal to function transformer, and pass the required parameters. Third step after initialization is perform the actual transformation. So we're gonna use from the function transformer library, which is transform. This is the simple function we are gonna use, and this one function is gonna do all the magic for us. For this variable, we're gonna pass the variables, input for which we want to perform the transformations, and in return, this will give us the new transformed values. Alright, what type of transformation you want to perform, that is mentioned here in the parameters while initializing the function transformer. And finally, we plot the histogram and QQ-plot to see the transformations using matplotlib and scipy. Okay, before we proceed and discuss in detail, if you are new here, don't forget to hit that subscribe button and the bell icon so that you won't miss our latest videos on AI. We see you are watching our videos, but 90% are not yet subscribed. We put lot of efforts creating these videos for you free. Keep us motivated by liking and subscribing, so YouTube algorithm will also help us reach more audience. So did you subscribe and like? Thank you. Okay, let's jump on the Jupyter Notebook now. Alright, here I am inside the repository. So we are in the feature engineering. So let me open feature engineering, and you can see we have seen bunch of different demos on the feature engineering prior. Missing data for creating new features, mean, median, categorical encoding. Now we're gonna talk about feature transformation using sklearn. Okay, let's open this one. Okay, so here in this video we are performing function transformations and the power transformations, and the dataset that we are using is California housing dataset. These are the characteristics of dataset that you can see. The attribute information is already given here. MEID INC stands for medium income in the society. House age, average rooms, average bedrooms, population. We are very much aware about this dataset already, right? And we're importing this dataset from sklearn dataset itself. Okay, so let's perform the first transformation, logarithmic transformation. First thing first, not to forget, import the libraries. I'm gonna use NumPy for statistics, Pandas for data frame, Matplotlib for plotting, and SciPy for scientific plots, which is QQplot, right? And the dataset that I'm using is from sklearn California housing dataset, right? I'm using it directly from the sklearn. And importantly, not to forget, the function transformer. This is why we are here, right? And again, we are importing it from sklearn, pre-processing, function transformer. This is the library we are using. After this, we are loading California housing dataset in X and Y, X input, Y output, right? And let's print the dataset here. After execution, and let's display the first 5 rows here. You can see this is how the data looks like. So just by looking at this data in the numbers, it is very difficult for humans to understand if data is distributed, if data is skeeved, not skeeved, very difficult, right? So that's why we take help of plot. Thumb of a rule is, whenever you get the data, plot the data, isn't it? That's why I'm gonna use the histograms and QQplots to understand the nature of the data. And we will be plotting it again and again for all different types of transformation. That's why we have created the function here, which takes data frame and the variable for which you want to draw the histogram and the QQplot. Here you see we are using Matplotlib and drawing the subplots, and on the data frame, this hist function will create a histogram for us. And same for the QQplot here, we are using stats probability plot here, defining for which variable we want to draw the QQplot, and finally using Matplotlib so that we can draw the QQplot. This is it. For now, let's try using this function and see the nature of the data without using transformations. So I have called this function by passing the raw data which we received here when we imported our data, and the variable which I want to consider is median income in the society. And when I draw the plot, this is how it looks like. Do you see this? The histogram shows the data is not Gaussian. Data is positively skeeved, right? It doesn't look like a bell curve. And similarly in the QQplot, I can see data is not much linear, it is curved, and hence it's gonna affect the accuracy of the model if I use these data as it is. Okay, so I have to make sure data is unbiased, data is Gaussian, and I have to make data normalized, and that's why I'm gonna use the very first transformation, which is logarithmic transformation. Let's consider the variables for which I want to use the logarithmic transformation. These are the variables on which I'm gonna perform logarithmic transformation. Now before I perform any operations, let me take the copy of input values, that is X copy. I'm creating just the copy of the values so that the original data set doesn't get affected, and this is the most important step that we need to perform. We did the import and we are gonna initialize the function transformer and pass the required parameters here. What transformer we are using here? A logarithmic transformer, right? So that's why function is equal to np.log. NumPy provides us different mathematical operations to perform, right? So np.log I'm using, this is the function I'm using here, and I'm also performing inverse of these values by using np.exponential, just to convert the variables into its original form. Okay, this is the variable where we have initiated. Now I'm going to use a very simple function here, which is called transform on the variable transformer, and pass for which variables you want to perform this log transformation. And in return, I'm going to get the variables which are transformed as mentioned. And now next thing is, let's plot it and see how does the data look like now. Again, diagnostic plot, right? So for the diagnostic plot, the new transformed variables, and for which variable, which exact column, right? This is the column we have seen. So just to remind you quickly, let me show you Before performing transformation, this is how it used to look like. Look at the data. This is positively skewed. Look at the distribution and look at the QQ plot here. Data looked little curved, right? It is not in line with this 45-degree line here. And after performing transformation, let's see the output here. What do you see? Amazing, right? Data is very much Gaussian, normalized, and in line with the 45-degree. Okay, so see here again. So this is before, this is after. Simple, great, right? This is the power of transformation. All right, if I want to inverse this or get the original values, then I'm gonna do the inverse transform on the variables and again do the plotting, right? So you see this is before, this is after, right? Same thing. So let's assume if your variable contains 0 or negative numbers, then how do you perform logarithmic transformation? It's very much important. If you know, logarithmic transformation can only be performed on the positive numbers, right? So if your data contains zeros or negatives, then I need to add the constant. And let's see how do I do that. If I have negative values or zeros, then I'm gonna use the lambda function here. Okay, same thing, take the copy, use the function transformer, and in the parameters, what I'm gonna pass is np.log plus 1. So this is the constant value that I have added, x plus 1. For each variable, lambda is used. It's like an inline for loop, right? So I have used lambda function to add constant for each variable, which is 1. All right, so I have initialized the transformer, and now I'm going to use the function called transform and get the new transformed variable list. And let's plot this using the function diagnostic plot, which we initialized here at the start, right here, which eventually draws histogram and the QQ plot. Okay, so the output here is not much different because we just added a constant plus 1 here, right? So that's why the output is very much similar, right? We didn't really require to add the constant plus 1 here, but just to show you the demo, how do you work with negative values and how will you add the constant if logarithmic transformation you ever use. Okay, let's proceed for the next one, the reciprocal transformation with scikit-learn now. Here we are using column called average occupation. It's nothing but average number of members in the house. Okay, and we are plotting the histogram and the QQ plot for the same, just to check how it looks before and after. It is not at all distributed. Data is highly biased. Okay, it is not normalized data in any way. Okay, so let's perform reciprocal transformation on this. I'm gonna use the same function, which is function transform, but only difference that you see is this. Rather than np.log, I'm using np numpy.reciprocal. This is the only change I'm gonna do, right? Rest of the things remain same. Transformer.transform, pass the column for which you want to perform the transform. This is the transform variable. Now let's plot the new transform feature here, which is average occupation. So if I execute this, you see at least data distribution is improved to some extent, right? This is after performing reciprocal transformation, and before performing transformation, this is how the data used to look like. Not distributed at all, very bad. And here at least I see some linearity or at least some distributed data after performing transformation. Definitely after transformation, this machine learning model will definitely provide me more better accuracy and the performance, right? Hope you understand how we are performing transformations. What we are doing here are the very simple steps, right? Import the library function transformer, initialize the function transformer, pass which type of transformer you want to use, log, reciprocal or square root or power transformer, and then use one function which is nothing but transform. And the new data, new column will be completely transformed for us. And finally, we are plotting QQ plots just to see how data looks like before and after the transformation. Okay, so if you are good till here, let's proceed and talk about the next transformation, which is square root transformation. For the square root transformation, we have created the data set, data frame here of count 1 and count 2 of this size, right? So we have 2 columns and these many rows here. You can see the data here. We have printed the data. We have displayed the top 5 rows here. Then I have taken the copy of the data frame and performing the function transformation. Nothing different. It's absolutely same. The name of the transformation itself is square root transform. This means I'm gonna take a square root of each feature here, and the same thing we are doing here using lambda function so that I can apply square root on each row, on each value, np.square root on each data set and round it till 2. And round the value till 2 decimals by using np.round and using lambda to perform on each and every value that we are going to pass in the data set. Okay, let's execute. And here using the transform function, passing the data frame count 1 and count 2 on which I want to apply this square root transform, and let's print the data to see how does the transformation looks like. This is how the transformation looks like after performing square root transformation. Don't worry about the plot here. We didn't perform this transformation on the housing data set. We created our own values here just to keep the simplicity. Important thing to understand is how did we apply square root transform here. This is the simple function that we have used. Talking about the most important transformation that I use generally are power transformations. Let's see how we're going to perform power transformation. We're going to see the demo for Box-Cox transform and Yeo-Jonsson transform. We have seen the demo for these three types already, right? So let's see how it goes. Coming back to Jupyter Notebook, I'm using these two variables, average income and the population. These are the variables on which I want to perform the transformation, taking the copy of the data set, and importantly, nothing different, using function transformer library here. As name says, power transformer, that means np numpy.power. In this case, we want to power every variable with 0.3. It is user defined. You define what is the power that is required for each variable, right? So we want to apply power for each variable. That's why we used lambda function here, and this is how we initialized our function transformer to perform power transformation. And nothing different, using transformer.transform function on the input variables which I have initialized here, and finally I'm gonna get the data frame of transformed variables. Let's see how it looks like by plotting the data using diagnostic plot for median income column, and also we plotted it for population. So this is the output that you see after performing power transformation. Do you see the transformation? The data is very much Gaussian and normalized, and also in the QQ plot I can see data is very much in line with the 45-degree line here. And if you remember, this is the same variable we used at the start of this demo, right? And before performing transformation, how it used to look like, let me scroll a bit above and show you. See, for median income column, this is how it used to look like. QQ plot is curved, data is not distributed. This is before, and this is after performing QQ transformation, where it's gone. Yeah, this is where you see. And you see a huge improvement in the normalization. That's the power of data transformation. Okay, last but not the least, let's see what is Box-Cox transformation. Okay, so that's the power of using user-defined transformation, nothing but the power transformation. Now let's see the very specific transformations which are really used in the real life, nothing but Box-Cox transformation and the Yeo-Jonsson transformation. Okay, let's see them, how it looks like. Alright, for the Box-Cox transformation, we are considering only the specific columns here, dropping latitude and longitude. Okay, and let me print the initial 5 rows and plot the histogram for all the considered columns. Okay, we just dropped these two columns, latitude, longitude, just to reduce the number of plots here. Okay, so we can see 6 histogram plotted here for the 6 columns, right? So you can see here, this is before performing transformation, not so Gaussian, positively skewed. This one looks like a normal distribution, very bad distribution, very bad, very bad, very bad for all other columns, right? Let's see after performing transformation, how does these variables look like. Let's convert the variables in the form of list so that it becomes easier for me to draw the QQ plot again. So we are just drawing the QQ plot here by using probability plot and show the QQ plot. Okay, so if you see, QQ plot looks something like this, right? Data is not so linear, not in the 45 degrees, not so linear again, not so linear again, not so linear again, right? By looking at this, I can easily understand only for house age, data is unbiased and Gaussian, but for other columns, it is not. So let's perform the transformation to see before and after performing transformation. So again here, I'm using the same thing, which is power transformer. What is the method that you are using? And trust me, these are more easier now. So I just want to define the variable, method, and provide what type of transformation you're going to use here, and use the function called setOutput so that you can convert the transform into the pandas data frame. Once the initialization is done, rather than using transform function, we are using fit function here. You see, we are not using transform, we are using fit function. So in short, the initialized transformer will learn from the lambdas that you have provided. Okay, learn from the lambdas that you have provided here. So I'm using transformer.fit and all the input variables which we have defined initially. If you want to see the lambdas, it's very simple. Transformer.lambdas, you can see something like this. So this is the array of lambda that you see here. And finally, use transform function to transform our raw data to the Box-Cox transformation. transformer.transform, the function transform, and the input value, and I'm catching it in new variable. Let's print the dataset, how it looks like. The new transformed variables, the lambdas you can see here in the table. And finally, without plotting these columns, I don't understand. So that's why let's plot the histogram and see how it looks like. Do you see, after the transformation, the output is much better, isn't it? You see, this is after performing Box-Cox transformation, right? Look at these graphs. Data looks Gaussian, unbiased, right? Normalized. And if you see here, before performing transformation, this is how it used to look like. Okay, you can just pause the video and compare these two graphs, right? And let's plot the QQ plot to see how it looks like. Great. Do you see a 45-degree and data is in line with this red line? So this is after performing Box-Cox transformation, and this is before performing Box-Cox transformation. Pause the video and yourself compare these plots, right? Before and after. Great. Now last but not the least, which is Yeo-Johnson transformation. Again, the most popular transformation out of all transformation, I would say. How we gonna use? It's very simple. Again, power transformation, again power transformer library, and only one thing that we need to mention here, rather than Box-Cox, the method is Yeo-Johnson transform. We did the initialization, set the output to pandas so that I can get the data in the pandas data frame. After initialization, not to forget to use transformer.fit the raw data. Now this will help learn the lambdas, meaning this transformer will be applied on every variable, and you can see the lambdas here by using the variable called lambda. You can print the lambdas by using transformer.lambdas variable. This will give us the array, and after this, let's use the transform function, which will actually help me perform transformation from the non-Gaussian data, positively skewed data, to Yeo-Johnson transformation. And let's print the data set here. This is how the data set look like. And not to forget, let's see the output by using matplotlib, histogram, and the QQ plot. Definitely you can see after performing Yeo-Johnson transformation, the output is much better, meaning data is very much Gaussian, data is very much inline, distributed, unbiased, right? So eventually it will help boost the performance of our model. Alright, this is it for this video. We have seen the demo for all the different types of transformers, function transformers, and the power transformers.
And that's how we come to an end of this video. If you have any questions regarding the same, let us know in the comment below. If you found this video helpful, please subscribe to my channel and hit the like button, and don't forget to share this video with your friends and the colleagues. Thanks for watching. See you again next time. Till then, take care and bye-bye.